Hello, I am HYU. Today I will talk about distribution-free predictive inference for regression. Um, so this is the paper is wrote by Jin Lei and several others writing 2018. And also in this report I also reference to this talk. Yeah, and I use it in some of my items. And this is a very good talk, so you also can see the slides from this talk. Okay, so today we'll talk about, first we'll talk about introduction and some notations, and some conformal inference, and its statistical accuracy. And we'll have some empirical study here. And also we'll talk about some extensions of conformal inference. And last we'll talk the conclusions. So we consider IID regression data Z1 to Zn, which is in a distribution P, where each Zi is a random variable comprised of the response variable yi and the d-dimensional vector of feature xi. And we let mu x equals to expectation of y given by x, and x denotes to the regression function. And we are interested in predicting a new response yn plus 1 from a new feature value xn plus 1 with no assumption on mu and p. So we are given a nominal miscoverage level alpha from 0 to 1, and we seek to construct a prediction band C based on Z1 to Zn with the probability that the probability of yn plus 1 belongs to the prediction band is larger than 1 minus alpha. And where the probability is taken over the n plus 1 IID draws Z1 to Zn plus 1 with p distribution. And for a point x, we denote like cx is equal to y belongs to R and xy belongs to C. So the basic idea of this one is like this. So if we let u1 to un be IID samples of the scalar random variables, and for a given miscoverage level alpha and another IID sample un plus 1, so we know that the probability of un plus 1 smaller than q hat 1 minus alpha, and this probability is larger than 1 minus alpha. And we define a simple quantile q hat 1 minus alpha based on u1 to un by the mu with order with n plus 1 times 1 minus alpha with cell function. So now we define Ryi equals to the absolute of yi minus mu hat y xi, and Ry n plus 1 equals to the absolute value of y minus mu hat y xn plus 1 as fitted residuals. So the next one, we talk about conformal inference. So for each value y belongs to R, we construct an augmented regression estimator mu hat y, which is trained on the augmented data set Z1 to Zn and xn plus 1 y. So we rank Ryn plus 1 among the remaining fitted residuals Ry1 to Ryn. So we're computing pi y equals to this one. And that means the proportion of the points in the augmented sample whose fitted residuals is smaller than the last one. So by the exchangeability of the data points and the symmetry of mu hat, so we evaluated at y equal to yn plus 1. So we see that the construct statistics pi yn plus 1 is uniformly distributed over the set the 1 divided by n plus 1 to 1, which implies that the probability of n plus 1 times pi yn plus 1 is smaller than 1 minus alpha times n plus 1 with self function, which is larger than 1 minus alpha. So we also can see that 1 minus pi yn plus 1 provides a valid p-value for testing the null hypothesis that H0 is yn plus 1 equals to y. So by inverting such a test over all possibility values of y belongs to R, the probability immediately leads to conformal prediction interval at xn plus 1. That means the conformal prediction interval of xn plus 1 equals to y given by n plus 1 times pi y n plus 1 smaller than 1 minus alpha times n plus 1 with self function. So the theorem below is talking about that if the data from 1 to n are IID, and for a new IID pair xn plus yn plus 1, so that the probability of yn plus 1 belongs to this conformal prediction interval is larger than 1 minus alpha. Yeah, here's the typo. Okay, so also we assume additionally that for all y belongs to R, the fitted absolute residuals of what are yi have continuous joint distribution. So it also holds that the probability of yn plus 1 belongs to this conformal prediction interval is smaller than 1 minus alpha plus 1 divided by n plus 1. So the algorithm is that we have input for data xi, yi for I equals to 1 to n, and miscoverage level alpha, and regression algorithm, and the test data at which to construct prediction intervals, and the value to act the trio values. So the output will be prediction intervals at each element of the test data. So we let every test data X to do so we built the regression algorithm for x1, yi to xn, yn, and the test data, and we'll construct and we'll find the residuals, and then we'll get the pi y, and so that we can get the conformal prediction interval, so we can get a conformal prediction interval, and then we can do for every test data, and we can do like this loop. Okay, so the original conformal prediction method is computationally intensive, because for each test data, we need to retrain the model on an augment data set, which includes the new data and recompute and reorder the residuals. So the next method we talk about is the split conformal. So the split conformal method, it separates the fitting and ranking steps using the sample splitting, and its computational cost is simply that of the fitting step. So that means the splitting improve dramatically on the speed of conformal inference, but introduce extra randomness into procedure. So this is the algorithm. So we also have the data XIYI and miscoverage level, and the regression algorithm, and we predict, and the output will be a prediction band over X. So first, we randomly split data into two equal size subsets, L1 and L2. So L1 will be a training data. The L2 will be the regression data, which is doing the ranking things. Yeah. So we get the regression. So we get the regression algorithm mu hat by the training data, and we can find the residuals with the celebration data, and we find the D, which is the k smallest value in Ri, where k is the steady function of half n plus 1 times 1 minus alpha. So we can get the interval of the split conformal prediction interval, like this one. And also we can get the theorem. This is a similar theorem from the theorem 2.1. So that we can get the yn plus 1 belongs to the split conformal prediction interval is larger than 1 minus alpha. Also, if the residuals have a continuous joint distribution, then this probability will smaller than 1 minus alpha plus 2 divided by n plus 2. So we can, based on the split conformal prediction, so we can get the multiple splits. So the goal of the multiple splits is to combine the inference from several splits. Is a way to reduce the extra randomness. So suppose that we split the training data n times, so yielding the split conformal prediction intervals from C split 1 to C split n, where each interval is constructed by the level 1 minus alpha divided by n. So we define the multiple splits is the is a we will find the joint of this conformal prediction intervals. So by a simple Bolzoni type argument, the prediction band has marginal coverage level at least 1 minus alpha. So the other one is the jackknife prediction. So this method uses the quantiles of leave one out residuals to define the prediction intervals. So An advantage of the jackknife method over the split conformal method is that it utilizes more of the training data when constructing the absolute residuals, and subsequently the quantiles. And the computational complexities is between the full and the split conformal methods. But the disadvantages is that these prediction intervals are not guaranteed to have valid coverage in finite samples. So the jackknife method has the finite sample coverage property is that the yi belongs to these intervals is larger than 1 minus alpha. So the algorithm is that given, so the input will be the data, miscoverage level, and regression algorithm, and the output will be the prediction band. So we for that every data, and we feed the data. We feed the data that shows that mu hat minus I, which means we train the data. We train all the training data without the XIYI, and we get the Ri. That's the residuals. So finally, we can get D, which is the k smallest value in R, where k is a cell function for n times 1 minus alpha. So, and then we can return for this conformal prediction interval. So, okay, so the next part will be the statistical accuracy. And before we're talking about that, we have two assumptions. The first assumption will be IID data. So we observe the IID data from common distribution P, and with mean function mu x is equals to the expectation of y given by x. And the assumption 1 is an independent and symmetric noise. So like for x, y belongs to distribution P, the noise variable epsilon equals to 1 minus mu x is independent to x, and the density function of epsilon is symmetric about 0 and non-increasing on from 0 to infinity. So we have two types of oracle. The first is the super oracle. It has a complete knowledge of the regression function mu x and the error distribution. And the regular oracle has knowledge only of the residual distribution. That means the distribution of y minus mu hat n x. And where xy belongs to distribution P is independent of given data xi, yi, and used to compute the regression estimator mu hat n. So we can, from assumption A0 and A1, imply that a super oracle prediction band will be like this: mu x minus q alpha, and the mu x plus q alpha, and the q alpha is the upper quantile of the epsilon. So also this band is optional in the following senses. The first one is it has a valid conformal coverage. Like the probability of y belongs to interval given by x is larger and equal to 1 minus alpha. And the second one is it has the shortest length among all bands with conditional coverage. Also, it has the shortest average length of bands with marginal coverage. So, also with the base fitting algorithm, AN, and a sample of size n, in order to have a valid prediction, the band needs to accommodate randomness of mu n and a new independent sample xy. So the oracle band will be the mu n x minus q n alpha and mu n x plus q n alpha, and where q n alpha is the upper quantile of the recitals. Here's a typo here. The n will be here. Okay. So the main theoretical results can be summarized to 3 things. The first one is to comparing the oracles. That means if the base estimator is consistent, then the 2 oracle bands have a similar length. And the second one is oracle approximation under stability assumptions. So that if the base estimator is stable under resampling and small perturbations, then the conformal prediction bands are close to oracle band. And the third one is super oracle approximation under consistency assumptions. That means if the base estimator is consistent, then the conformal prediction bands are close to the super oracle. Okay, so the first thing is talk about comparing the oracles. So intuitively, if the mu hat n is close to mu, then the 2 oracle bands should be close. So we denote the estimation error as the triangle nx equals to mu hat nx minus mu x. So the following theorem is talking about the comparing the oracle bands. So we under the assumption A0 and A1, and let capital F and smaller f be the distribution and the density function of absolute of epsilon. So we assume further that f has a continuous derivative that uniformly bounded by m is larger than 0, and that fn and capital Fn and smaller fn be the distribution and density function of the recitals. And we have the sup of f capital Fnt minus capital Ft have bounded with half of m times the expectation of triangle n with square. And the expectation is taken over a randomness of mu hat n and x. And if the lower bound, if f is lower bound by r is larger than 0 on q alpha minus this one and q alpha plus this one, and this will be larger than m divided by 2r times the expectation of triangle n with square. So we can get the q n alpha minus q alpha is smaller than this one. Okay, so the second case will be oracle approximation under the stability assumptions. So we can put into 2 cases. The first one is split conformal case, and the second one will be full conformal. So we'll talk about split conformal case first. So And in here we have another assumption, which is simply stability. So for large enough n, and the probability of this one is smaller than full n for some sequence satisfying this one, and with some function mu type. And because this is the stability assumption rather than consistency assumption, we only need the estimation. We only need the estimator to concentrate around the mu type. Okay. So when assembly stability fails to hold conditionally on mu hat n, the residuals may have a substantially different distribution than Fn, and the split conformal interval can be substantially different from the oracle interval. So this theorem is talked about. We fit the alpha and we let Cn split and Vn split denote the split conformal interval and its width. So we under assumption A0, A1, and A2 assume further that F tight and the density of residuals is lower bounded away from 0 in the open neighborhood of its alpha upper quantile. So then the Vn split minus 2Qn alpha equals to operation with this one. And another one is the full conformal case. So we recall that for any candidate value y, we will fit the regression function with augment data, where the n plus 1 data point is xy. So we denote this fitted regression function by mu hat n xy. So we have another assumption, it's called perturb 1 sensitivity. So for large enough n, and the probability of this one is more and equal to full n, and for some sequence satisfying this one as n becomes to the infinity. So also the theorem is talk about similar things. Yeah. Okay. So the next part will be the super oracle approximation under consistency assumptions. So we also get another assumption A4, which is consistency of base estimator. So for large enough n, we can get a probability of this one is smaller than full n for some sequence satisfying for this one, thus n becomes to infinity. So also here has the definition of asymptotic conditional coverage. We say that the sequence Cn of the random prediction bands has asymptotic conditional coverage at the level y minus alpha if there exists a sequence of random sets and such that a probability is equals to 1 minus operation 1, and the infinity of this probability minus 1 minus alpha equals to operation 1. So we will show that conformal bands are close to the super oracle and have approximately correct asymptotic conditional coverage. So the theorem 3.4 is talk about the split conformal approximation of super oracle. So we under assumption A0, A1, and A4, assuming the addition that the residuals has density bounded array from 0 in an open neighborhood of its alpha upper quantile. So the split conformal interval satisfies than this one. And LA denotes the Lebesgue measure of the set A. And A triangle B is a symmetric difference between sets A and B. So thus the C split has a asymptotic conditional coverage at the level 1 minus alpha. And the theorem 3.5 is talking about the similar things. Similar things about the full conformal approximation of supervertical. Okay, so next we'll talk about comparison to, we'll talk about some empirical study. And the first one will be comparisons to parametric intervals from linear regressions. So in this one, we empirically compare the classical parametric interval and conformal intervals, which is full conformal, split conformal, and jackknife interval conformal from a linear regression in both low dimensional and high dimensional problems. With the three following settings. The first one will be linear, and the arrow is also linear. And the second one, the second one is similar, but the mu x is nonlinear, and the arrow have a higher tails. And the third one will be linear, but with a mixture with several distributions. So in the low dimensional case, the full conformal interval is shorter than the split conformal interval, but it comes at a higher computational cost. And also the jackknife interval has a shorter average length at a reasonable coverage. And in the high dimensional cases, it has a poor accuracy of linear regression estimation when D is large. So in this paper, you will put the rich regressions, which improve the performance of all methods. And also the split conformal method exhibits the clear computational advantage compared to the full conformal method with similar performance. So we can see in the paper, this is the cases for lower dimension. So we can see the full conformal, the average length of full conformal, is shorter than split conformal. See, and the jackknife has the smallest average interval. Yeah, and we can see the computation time. The computation time for full conformal is more larger than the other two. Also, this is the comparison of the high dimensional cases. We can see only here is only for full conformal and jackknife. That is because for split conformal, you only have 250 for training, but with 490 dimensions, which is undefined for linear regression. So here we only for full conformal and jackknife. And we can see we have the poor outcome for coverage and this average length. So this table is we use the rich regressions to instead the linear regression. So we can see this is This is better for both coverage and average length. And also, it is still computational for the full conformal than the split conformal. And and also we can see the jackknife of its average length is also shorter than the other two. Also, the second case will be comparison of conformal intervals across the Bayes estimators. So we also use the simulate data from settings A to C in both low and high dimensions. And in each case, we apply 4 stepwise regression, lasso, elastic net, sparse additive models, and random forest. All curving figures presents that an average over 15 repetitions, and we use the split conformal methods for computational efficiency. So we can see the best test errors are obtained by linear methods, the lasso elastic net stepwise in a linear setting A, and by SPAM in a nonlinear setting B. And all estimators perform quite poorly in setting C. And in high dimensional cases, the results are similar. And the SPM looks a little better in setting C. So also across all settings and estimators, no matter the performance in test error, the coverage of the conformal intervals is almost exactly 90%. The nominal level and an interval that seems to be highly correlated with test errors. So we also can see from the paper here. So this is the low dimensional case. And we can see the linear cases will be better in setting A, and the SPM looks better in settings B, and all of them seems to be poorly in setting C. And also this is the higher dimensional cases, and it also has the similar results. And you can see the SPM seems a little better in setting C. Okay, so the next one we're talking about some extensions of the conformal inference. The first one will be rank 1 out conformal inference. So these methods are designed to give a valid prediction intervals as a future point x plus 1 from the same distribution as in the same distribution, but it is not yet observed. That means we do not have a finite sample guarantees. So the basic idea is quite similar to split conformal, but the ranking is conducted in a leave one out manner. So the ROO split conformal intervals have a in-sample finite sample coverage property for this one. So the algorithm is that given the data xi, yi from I to n and mixed coverage level alpha and the regression algorithm. And we also randomly split into 2 equal size subsets, L1 and L2. So for every for L1 and L2 respectively, we do the mu k, and then we get the residuals we get the residuals, and then we find the di, which is the m smallest value in Rj, and j is not equals to I, and m is equals to the cell function of half of n times 1 minus alpha, and then we can get the intervals. And the following theorem is talking about for given absolute constant c, and such that for O epsilon larger than 0, and the residuals is joint distributed, so that the probability of this one is larger than 1 minus 2 expectation of this one. Okay, so the next one is locally weighted conformal inference. So when the noise is heteroscedastic, we can replace absolute residuals by locally weighted versions, like this one, and where sigma hat n squared is the estimate of variance function of the absolute residuals. So the local width in the locally weighting prediction band can be very considerably, and it also seems similar to the split conformal cases. The interval will be mu hat x minus mu sigma times q hat, and the mu hat x plus the sigma hat x times q hat. And the q hat is a quantile 1 minus alpha with the residuals with infinity, and the mu hat and the sigma hat are fitted with d1. Okay, so the conclusion will be also okay. So the conclusion, the conformal inference is a way to use symmetry to provide distribution-free, finite sample prediction intervals, and these intervals have marginal coverage over the feature space, and getting the conditional coverage is much harder problem. And the split conformal is much faster and simpler, has the same guarantee. Also, there are some extensions such as ROO and locally weighted. So the better the base estimator, the shorter the prediction band. So for a consistent estimator, we get asymptotically the shortest band possible. So thank you. Thank you everyone. This is my talk.